Hello, and welcome to this Mobile World Live webinar, Unleashing Scalable Innovation with Programmable MEC. I'm Michelle Donegan, and I'll be your moderator for today's event. Today, we're going to be discussing a multi-access edge computing platform solution called CyberElastic that combines components from Intel, NoviFlow, Lanner, and Fortinet to address the complexity of implementing security at the edge. We have speakers here from each of the companies involved to walk us through this innovative solution. And before we get started, I'd like to encourage our audience to participate today. You can post questions at any time during the presentation, and we'll have time for Q&A at the end. And now I'd like to introduce our speakers. Joining us today are Prem Jonalagada, Senior Director of Product Management and Marketing at Intel, Sven Freudenfeld, Chief Technology Officer for the Telecom Applications Business Unit at Lanner, Jesper Eriksson, VP of Product Management at NoviFlow, and Nicholas Thomas, a standards MANO and VNF strategist at Fortinet. So now let's take a look at a quick look at today's agenda. So we'll start with an overview of the Programmable Network Fabric. We'll describe the Converged MEC Smart Edge platform. We'll also talk about the network operating system, operations and maintenance, and the MEC platform software. We'll discuss the virtualized scalable security software, and we'll hear about some use cases as well. And with that short introduction, I'd now like to hand over to our first speaker, Prem Jonalagada from Intel.
Thank you very much. Now I'm going to cover BAREFOOT technology and products. Before I do that, I just want to talk about this general industry trend towards domain-specific architectures. As you can see, in the compute industry, graphics industry, signal processing, or machine learning, there's this convergence towards a domain-specific architecture. Now, what do we mean by a domain-specific architecture? Typically, when you have a domain-specific architecture, there's a high-performance target device like a CPU, GPU, digital signal processor, or a tensor processing unit. And then there's a high-level domain-specific programming language. A few examples are shown here. And these two things are brought together by a compiler. So if you look at the networking industry, this trend has been missing until BAREFOOT came on the scene. So what we have done at BAREFOOT is not only have we created a compiler target, which is domain specific to networking, we've also helped create a high-level programming language called P4, and then we have actually developed the compiler to bring these two things together. The reason a domain-specific architecture is important is because it actually puts the power of the whole technology into the end user's hands. And it also helps vendors to create innovative solutions to their customers. So I've talked about two key components. One is the programming language itself, and the other one is the actual compiler target. So let's look at the programming language. P4 is a high-level domain-specific programming language that is geared towards packet processing. P4 stands for Programming Protocol Independent Packet Processor. It's a mouthful, but P4 is exactly what it is. It's a high-level programming language for programming protocol independent packet processors. As you can see from the snippet of the code on the left, it's looks like C. It's easily readable, and it has constructs that are packet processing specific. So as you can see, there are things like headers, tables, actions. These are all very packet processing specific constructs. And the reason it is constructed this way or designed this way is because it enables networking software developers, networking system developers to write really efficient packet processing code. Something that would take probably hundreds of thousands of lines of code in a general purpose language can be written in tens, hundreds, thousands of lines of code in P4. So it's very efficient, very accurate. There's no ambiguity when you write code in P4. So it allows for, an easy way to describe packet processing. Now, the best part about P4, it's an open language. It's an open source language. It's built by the community, and it's a growing community. We have seen that there's lots of trainings that are happening across the globe, roughly over 4,000 and counting, probably even 4,500 now. Developers trained through various training programs. There's training programs that we offer. There's hackathons and training programs that are going on all over the world. So it's really powerful to see this community grow and really enable new innovations in networking, because P4 is there. So not only is the programming language growing and a lot of people getting trained, there's more and more vendors adding support for P4. What do I mean by that? Basically, there are companies that are developing switch ASICs or SmartNIC ASICs that are now programmable using P4. They have P4 compilers out there, and you can program these devices using P4. So just goes to show you that this ecosystem is fully open, and there's more and more people, not only from consumers, but also producers coming into this ecosystem. So now that I've described P4 a little bit, I want to talk about some of the technology that BAREFOOT has created in the switching space, and the Tofino switching ASICs that are actually used in the Lanner platform, so that we're going to be looking at. But here's a quick snapshot. Tofino and Tofino 2 are P4 programmable switching ASICs that are going from 1.2 terabits per second all the way to 12.8 terabits per second. And this goes to show you there's multi-generational products that are using P4, and also not compromising on performance. Now, whenever you have a programmable device, you need to have really rich tool set or toolkit that goes with that programmable device. And so we have invested heavily into our software toolchain, P4 Studio and P4 Insight, our compiler and debug tools that are available for our Tofino customers to be able to take advantage of the power of programmability that Tofino offers. So this is very important, because if the target is programmable, but the associated toolchain is poor, it really doesn't let you take advantage of the target. So we made sure that we created all the tools that are necessary for our end users and customers to take advantage of this powerful programmability that's available in Tofino and Tofino 2. One of the killer apps of programmability is visibility, and so we also help create a product called Deep Insight, which is a collector of real-time telemetry, helps network operators to visualize this telemetry in real time to kind of find out what's going on in the network. Where are the problems happening? Where are bottlenecks? Are there any packet drops happening? So things like that. So really enabling efficiencies in the network through visibility. So that's a quick snapshot of all the different products. Now let's look at how the actual switch systems are built and what are some of the applications, some of which will be discussed later on. So if you look at a typical switch system, it kind of looks like that big blue box in the middle here, the switch platform, and it typically contains a switching ASIC and a control plane processor, typically an Intel Xeon processor, and you can actually develop all the P4 code and the associated software that's needed on a separate server platform, and that's this box that we're showing here. You can also develop the P4 code on the control plane processor itself if it's powerful enough. But for simplicity's sake, I'm showing the development happening on a separate server. People can develop all kinds of applications, leaf spine, switch, L2, L3 functionality. You're seeing people develop network packet brokers, load balancers, even traffic testers. to be able to test, generate multi-terabits of traffic to test your networking devices or networks. Things like cloud gateways and then UPF and BNG and other emerging use cases that are coming into the market. So just goes to show you the power of the programmability of Tofino and Tofino 2. Another interesting development that's happening is people are actually pairing Tofino and Tofino 2 with an FPGA to be able to deliver even richer functionality with whether it's extending tables or doing interesting traffic management capabilities. Now with Xeon, Tofino, and an FPGA, you can build a really powerful platform that actually serves all your different needs. Now, all of this is happening while we're not compromising on performance or power. So, for example, we compared a Tofino platform with an equivalent platform based on a fixed function ASIC, and we saw that the Tofino platform performs 14% higher in performance, and then actually consumes 14% lower in power. So just kind of shows you the architecture and the benefits of Tofino, where we're delivering programmability with all the performance you need without any penalty on power and other things or latency. So really what this is going to do is the benefits will now be carried over into all the other areas of the network. The mobile edge computing platform that we're talking about is focused on the edge side of the network, but the dynamics and the economics of this solution are applicable in the core, in the data center, in the cloud, and even in the access side of the network. So we are committed towards enabling a P4 programmable fabric, and we're really excited to see Lanner, NoviFlow, and Fortinet take advantage of this programmability to deliver a compelling product for solving really critical challenges that networks of today and tomorrow are going to face. So with that, I'm going to pass it over to Sven from Lanner to continue the presentation.
Thank you, Prem. When we started looking at the network convergence, and we created this concept of a platform which is suitable for the service provider edge, we looked at different use cases. The fixed network and the mobile networks are very similar from an architectural point of view. It contains networking, routing functions, as well virtual network functions, using scalable appliances to deploy some of the network functions. For example, on the fixed network, we're looking at virtual carrier grade NAT, virtual firewall, virtual CDN, and other networking functions, which are basically residing on a white box or an agnostic server or hardware platform, which can then scale depending on the use cases deployed at the edge. On the right side, you see the mobile network, and the mobile network is very similar from a hardware point of view, from an architecture point of view. It's very identical. So you have a routing functions basically built into this. And in addition to that, you have all the networking function like MME, HSS, servicing gateway, and packaging gateway. These are becoming virtual appliances residing on a commercial off-the-shelf server platform. And typically, these are, single boxes, and they need a dedicated top-of-rack switch or a dedicated router in the past, and a dedicated appliance just to serve these network functions, and they are only dedicated for that one function. When we're looking at it and we want to consolidate the workload, and the trend is that the fixed and the mobile coexisting in the network, we need to find a platform which can be more scalable and more efficient to roll out these services. So the trend is that when you take a proprietary platform on the bottom left, these are all dedicated platforms for a dedicated workload. But this is moving towards a virtual network functions, and we came up with a platform which is sort of a white box, which contains all these functions for routing, networking, compute, and storage in a single box. You can see that sort of a mini data center in the box, which is residing at the networking edge. What's important here to know is that when we look at the three pillars, the local aggregation, the metro and the regional, as well the core network, networking functions are more critical at the aggregation layer because the aggregation is the most dynamic point for networking functions, meaning the traffic is more diverse than at the core, because at the core what you do is you create your networking routes and then you will not touch it for a while because these are all mainly fixed core functions. But on the aggregation point, you have incoming traffic, which could be IoT traffic, which could be coming from a cloud run appliance. It could be from a customer premise equipment or universal CPE. It could be an SD-WAN function residing at the edge. So, and the traffic is very dynamic. So you need to be able to reroute traffic more efficiently, and then doing some of the virtual network function right at the aggregation point, rather than waiting until you pass the traffic throughout the metro and the core, because latency is critical for some of the network functions. And initially, most of these aggregation points are consolidating the workload for, let's say, virtual broadband network gateways, but also for virtual provider edge, beyond the virtual CPE function. In addition to that, virtual EPC, virtual evolved packet core, may also coexist and reside on the same physical aggregation hardware as a virtual network function. So we need to be able to route the traffic very dynamically at the edge to identify what is the next available compute resource and where does it reside. So that's why programmability on the networking aspect at the aggregation point is very critical, besides the compute resources. So why did we choose BAREFOOT? Well, the BAREFOOT Tofino ASIC is a true open programmable ASIC for networking. Prior silicons are very locked in, they are very limited in terms of programmability and as well scalability. The introduction of P4 as a programming language, as well the capability of using an open programmable ASIC, gives much more flexibility at the service provider edge. In other words, we can actually use the P4 runtime interfaces in combination with an SDN controller and have a true software-defined networking appliance to scale networking and compute all together. And with the programmable edge, it allows us to identify the traffic flow, where it's coming from, what type of traffic, and where does it need to be routed. At the same time, this ASIC also allows to act as a load balancer for security offloads, traffic mitigation, and so on. So these programmability aspects are very critical at the edge. The most vulnerable point for the network is the service provider edge. That's why these elements are very critical in the network. Second point on this is why we choose BAREFOOT Tofino is that, of course, as Prem has highlighted, there are some network functions built into this ASIC which allows to do inbound network telemetry, which means that we get much better visibility on the overall network, right at the edge when the traffic hit the network. So we can do much better and smarter decisions on the packets, how they're going to be routed within the network. We have historical data, we're collecting data from the network. It's not a one-way direction. We're actually getting intelligence from the network, and we can then make decisions right at the edge, how we route traffic, where are my compute resources, and then reduce the latency right at the edge to be able to provide the services to the network, but also to the customers. And then the scalability aspect, that's the third point on that. It, as I said, it collapsed multiple functions, specifically for the load balancing function and traffic mitigation. We can very early in the entry of a network identify if it's a packet where it needs to be passed through additional DPI engines or virtual firewalls, and then it allows us to scale. So if I have an attack, I basically can scale up my compute resources because I can identify the packets early in the network, and at the same time I can learn from that packets that these are a created blacklist. That means the next time the traffic hits the edge, we can mitigate it immediately, and we're saving compute resources at the edge. And that's also a very critical aspect, and why we choose the BAREFOOT Tofino on the edge platform. Here, a couple of use cases. So we are engaged with service providers. You can see here that because this platform is completely integrated as a software-defined networking architecture, we can reside in multiple locations. Normally, the service provider edge could be, in the thousands or 10,000s locations all over the country. One of the use cases would be sitting in a telco closet in a multi-dwelling unit. That means that some of the network functions are going to be residing locally at these locations. Some of the network functions going to the edge central office, and maybe there's also a hyperscale play in offloading some of the network functions throughout the public cloud, or pass it through the network for other applications to be loaded. So that means that we offloading the cost for let's say universal CPEs. That means the need for a big box is no longer critical. We can shrink down the cost for the universal CPE or SD-WAN appliance, because we are doing traffic mitigation as well. We're doing some of the network functions right at the service provider edge. That means that we do a load balancing, as I said earlier. We are looking at security threats at the service provider edge, and it's all integrated. So we're saving the overall operations cost by a significant amount, because we're building a SDN framework, which is true software defined. So that means once the box is installed in this multi-dwelling units, anything else, provisioning, redirecting traffic, network telemetry, is all residing at the edge, and is all done via software defined networking. So that's a significant time and money savings for the operator, all the way down to potentially even provide a self-serve point. So that means that the ultimate goal will be that you're reducing the operations costs by actually making that available. And as it is a software-defined networking infrastructure, you can really scale up and scale down as you need it. Quick overview on the platform. It's a fully integrated modular platform that scales. We have multiple compute nodes. These compute nodes have different compute SKUs from Intel. They can be, starting from a, let's say, 4-core, 8-core, all the way up to a 28-core. Total number of cores will be in with 6U would be about 336 cores. We have a networking capabilities built in. On the top picture, you can see the two switches based on Tofino. The top two slots. Below the other four are the aggregation points. They are leveraging the Intel NICs directly connected to the CPU. And that will be basically the 1 gig or 10 gig port for a connection to, let's say, a universal CPE, or a baseband processing unit, or a centralized unit for Cloud Run. So these are all the capabilities of the platform. Full redundant power supply. It is carrier grade, meaning we have full HA features built in, also very important for edge deployments, and all shrink wrapped into a small footprint, fully integrated with 100 gig backplane connectivity to all the CPUs. And to Jesper.
Thank you, Sven, and good morning, everyone. My name is Jesper Eriksson, and I'm the VP of Product Management at NoviFlow. NoviFlow has ported 2 of its existing software products to the Lanner HTCA platform. The NoviWare NOS to the HTCA switchblades, and the CyberMap application to the HTCA compute blades. NoviFlow has also developed a new software product specifically for the HTCA platform. It's called VisualAnalytics and resides on one of the HTCA compute blades and also utilizes the mass storage. A few words about NoviWare. It's a mature SDN switching NOS that has been commercially available and in operation since 2014. It has a full range of modern O&M interfaces such as GNMI, GNOI. It supports the P4 runtime and OpenFlow northbound interfaces to configure and dynamically update the packet processing in the switchblades. It allows an application programmer to define a unique match action pipeline to match the requirements of his or her application. Next is CyberMapper, an application built on top of NoviWare in commercial operation with multiple carriers. On a high level, CyberMapper provides the following services: threat intelligence gateway services, traffic steering, packet brokering, filtering, sticky and stateless load balancing, SRv6 routing, and service chaining through SRv6. Finally, VisualAnalytics is a new standalone application from NoviFlow, first released on the Lanner HTCA platform. It provides an end-to-end view of the HTCA platform for hardware and software alarming and troubleshooting. It will simplify the O&M of the HTCA platform. With potentially thousands of these MEC platforms deployed in a carrier's network, you need a way to minimize truck rolls. And if you have to go to a site, be able to perform preventive maintenance. These are the problems that VisualAnalytics solve. This slide shows the components of the CyberElastic, a complete solution from NoviFlow built around the Lanner HTCA platform. Starting at the bottom is the Lanner HTCA hardware, leveraging the Intel BAREFOOT Tofino and x86 silicons. The 6 compute blades all run Red Hat Enterprise Linux, providing a commercially supported Linux operating system. The NoviFlow CyberMapper is one of the applications residing on the compute blades, providing load balancing of the FortiGate security cluster. The FortiGate security cluster resides on the compute blades and consists of hundreds of individual FortiGate VMs. The Red Hat OpenShift application also resides on the compute blades and provides management of the various containers and VMs on the compute blades. And finally, the NoviFlow VisualAnalytics resides also on the compute blades and provides complete end-to-end visibility of the entire platform, including the hardware, the operating systems, and the applications. This slide describes the 3 distinct ways that you may program the behavior of a network. These 3 ways are not mutually exclusive and are often used in conjunction. The first way to program a network is at the orchestration level. At this level, you program the configuration and state data of the network devices. The network device configuration state data is abstracted through a standardized data model, such as a Yang model, and then this data structure is then written or read from a controller using netconf or GNMI protocols. This way of programming the network is used when you have distributed switching and routing protocol stacks, and the match action pipeline is hidden behind these protocol stacks. The key benefit from this level of programming is to automate the provisioning of legacy network devices and to speed up the provisioning of new services and to eliminate manual errors during the provisioning. The second way is to program the match action pipelines of the network devices. A set of match action tables are programmatically defined through OpenFlow or P4. At runtime, a controller pushes flow entries into these flow tables using OpenFlow or P4 runtime protocols. The match action pipeline and the flow entries define how packets are processed by the network device. The application interacts directly with the match action pipeline in the device. The key benefits from this level of programmability is that entirely new types of network functionality may quickly be developed and deployed to solve new networking problems. and that the network device functionality may easily be modified and changed over time through software as the network evolves. The third way is to program the packets themselves. The technology for this is segment routing over IPv6 or segment routing over MPLS. As the packet enters the network, it is classified, and based on that classification, an ordered list of instructions are inserted directly onto the packet that defines how the packet will be processed by the network. There's a rich set of instructions already defined by the IETF, including instructions for providing traditional VPN services, but also new instructions for service chaining and proxying for virtualized network services. The key benefits from this level of programming are service chaining and making network services addressable from anywhere in the network. CyberMapper is built on top of NoviWare, the NoviFlow SDN NOS, and provides a number of network services that network operators need in their network. The Threat Intelligence Gateway service is a way for operators to block certain traffic from getting onto their network. CyberMapper will execute any deny list directly in the Tofino silicon and do so much more efficiently than on an x86. An example of a deny list is the deny list published by the Internet Watch Foundation. The packet broker services include things like filtering, mirroring, and port pairing. The load balancing services are built on top of a sticky and stateless load balancer implemented directly in the Tofino silicon. It supports proportional load balancing and the ability to dynamically grow or shrink the pool of load balanced VNFs. For the Lanner HTCA, the load balancer leverages the two NICs on each compute blade and uses SRIOV for maximum throughput performance. The network services include traffic steering and aggregation for scaling CGNAT and other services, in-band network telemetry for VNF performance monitoring, SRv6 routing and security service proxy that allows the VNF's resources inside the HTCA platform to be globally addressable in the network. The VisualAnalytics provides an end-to-end view of the hardware and software status of the HTCA platform. This simplifies the operation and maintenance of the HTCA platform and saves money. It avoids unnecessary truck rolls. Consider that a single truck roll may cost in excess of $1,000 per instance. It allows preventive maintenance to be scheduled to replace failing parts such as fans and power supplies. This is how it works. The VisualAnalytics software harvests thousands of data points every minute from the hardware, the compute blade operating systems, and the NoviFlow applications. The data is then transformed into its canonical form and ingested into a data lake residing on the platform. The data is then organized and visualized for easy troubleshooting. It allows you to identify key hardware and/or software events, correlate events, and drill down into specific events. The HTCA platform has multiple levels of redundancy built in. The Tofino switch blades are duplicated and operate in active-active mode. Traffic from the outside is load shared across the two switch blades using lag. If one of the switch blades fail, the traffic is redirected to the remaining switch blade. The CyberMapper application runs on two different compute blades in an active standby mode. And finally, the virtual security appliances run on the compute blades in an N+1 or N+M mode. If one of the VNFs fail, the traffic is redistributed across the remaining VNFs. We will now look at some of the MEC use cases for the HTCA platform. The first use case is to use the HTCA platform as a scalable security perimeter device. The HTCA platform may be deployed as a bump in the wire or as a routable member of an SRv6 network. What this means is that the security services are either hardwired into a particular location or globally addressable through the routed network. Traffic enters the HTCA platform through the Tofino switchblades and is load balanced across the VNFs. Capacity may be scaled up or scaled down dynamically. VNF latency is measured through in-band network telemetry. With the compute resources available on the Lanner HTCA platform, we estimate the following Fortinet firewall throughput performance. More than 900 gigabit per second of pure firewall, more than 400 gigabit per second of IPS, and more than 350 gigabit per second of firewall plus IPS. This next use case is an edge aggregation point. This use case is architecturally different than the previous use case because in this case, traffic enters the HTCA platform through the I/O ports on the front directly into the compute blades for processing. There is no load balancing needed. Each subscriber is connected to its own dedicated VNF, or in this case, Fortinet FortiGate. Once the VNF has processed the traffic, it is sent to the Tofino switchblade for forwarding further into the operator's network. With the compute resources available in the Lanner HTCA platform, we estimate more than 900 gigabit per second of throughput and the ability to support over 500 subscribers. The last use case I will describe is the SRv6 service chaining. Traditionally, security appliances have been hardwired into a specific location in the network and only available for traffic going through that location. SRv6 opens up a new way of programmatically inserting security services in traffic flows that are not tied directly to that specific location. In this use case, the HTCA platform operates as a security services proxy in a routed SRv6 network. A source router somewhere to the left in the picture will insert the segment routing header with a list of segments. And one of these segments represents a security policy that the packet has to go through. The source router then forwards the packet to the next hop. Once the packet has been forwarded to the HTCA platform, it will match the segment ID into a specific chain of security services residing on the compute blades and executes those services before forwarding the packet to the next hop. Lanner and NoviFlow are working with a major North American carrier and a tier 1 router vendor to build this architecture end to end. I will now hand off to Nicholas Thomas from Fortinet.
Hello, thank you, Jesper, for having me in this call. Fortinet in this environment provides additional service on top of the infrastructure, on top of the switches, etc., that you've been presented before me. We focus, as you know, Fortinet mainly on network security with the FortiGate. And our goal here was to be able to deploy scalable infrastructure on that top of that scalable infrastructure, benefit from it for advanced security. It can be anti-malware, DLPs, anti-phishing, etc. Can go up to sandboxing advanced threat protections. One of the use case for people like service providers who have that need for scalability and moving to MSSPs is what we call clean pipe. It's when you delegate to your service providers to take care of the security for you. So instead of having your own next-gen firewalls, you delegate that to managed security service providers. And we see that coming more and more. Also why we lead the MEC 88 specification, because it's really around those terms. And when you start to do this, you need the flexibility of the platforms to be able to deploy on MEC platforms mainly, and rapidly ramp up new customers. It's not acceptable anymore to spend 6 months to cable things. So this is where we really can benefit from the NoviFlow and Lanner combinations, where we can then have the connectivity to one side. It's very interesting because you can have a cable per customers, put the VMs on top, and provide the advanced services with all the flexibility, cloud-like flexibility you can have with the VMs. I will move on to the next use case, hopefully. CGNAT also is a very important part for telcos with the seasonability of the traffic. So this runs more in the core or close to the core than the far end of the edge. But it has some characteristic where scalability makes a lot of sense. First, a lot of traffic, and seasonability, where you have a lot of IPsec tunnels, but more importantly, some area, like let's take a stadium, for example. You will have a lot of people at some time during the day or during the week, and almost nobody the rest of the time. So, capacity management and all that, it makes a lot of sense to be able to have a scalable solutions that adapt to the traffic. And this is where we play a role with the CGNAT part on top of this type of infrastructure. And last, not least, the more interesting part for experts in our labs, in our joint labs, is hyperscaling, hyperscale type of capability for the clouds in general, but getting ready for the future type of traffics we're going to need, targeting the terabyte. Today, if you have one or a couple of VMs on one machines, you can maybe reach 100 gig on the NIC, and that's the maximum for a strong price. We saw with the NoviFlow being able to reach those levels, those terabytes levels, and spread the load to many different VMs. We did see jointly in labs doing real traffic that we can reach a very high level of traffic with a very good resiliency, because you have a N+1 model, N+M model for the VMs. So if you lose one, you don't lose half of the traffic. And have a very rapid reactions to change in the traffic patterns by delegating the load sharing to NoviFlow, where we get there. And we know we have more improvements in the pipes of the deployments. We already have the DPDK enhancement with the virtual NP on FortiGate VMs, where we do more than simply use a DPDK-driven NIC, so which just pass the traffic. We start to push down to the DPDK what we used to do in some of the functions we used to do in the in our own ASICs to get closer to the maximum performance you can get in theory from those machines. So all those things combined, the switching, the form factor, cabling, and our VMs and solutions on top makes for a great way to deploy very scalable solutions. And if you go more from an architecture point of view, it looks like this. You need to orchestrate those different pieces and parts. It's all done through APIs. And you can program the switch. And this is the part where we can really stitch together the load sharing and the capacity of the FortiGate VMs, which can use session sync and configuration synchronization between them, which means you don't need to put a double terabyte capable legacy load balancer in front. You can really leverage the full infrastructure and the ASICs up there and the P4 program realm to your advantage to reach unprecedented level of scalability in there that we never see for us. Thank you.
Thank you, Nicola. We just want to give a quick highlight on some of the service providers' initiatives and how this will affect a rollout. This is a very simplified diagram, from a network topology point of view. As I had mentioned, or as we had mentioned earlier, we have the endpoints, which are customer premise equipment, which are universal CPE, which can reside on a white box as well, but it's limited resources on a universal CPE. And there are some virtual network functions residing on that. Could be also a small scale firewall in a hybrid mode. Could be also some of the other enterprise communications applications, including LTE connection and 5G connection and so on. But the critical path is when you connect to the edge central office, because the growth of universal CPEs and the trend, what we have seen over the last 4 years, is that these are becoming much more adopted and much quicker adopted than we thought before prior COVID-19, because it's an increase on reducing the truck roll and moving towards managed services, because most of the enterprise is reducing the IT overhead costs and leveraging the cloud infrastructure. So therefore, the edge central office is the critical entry point of a network, and that's where the platforms are residing. This is a major service provider in North America who is leveraging the tools and the technology built into the platform to have low-cost data processing at the edge, but also introduce artificial intelligence and analytics right towards the edge. As I mentioned, the security aspect is crucial also at the edge compute platform. So ultimately, what are we trying to say? Basically, is that using a traditional architecture, which is purpose-built for each individual network function, switching, computing, load balancing, security, and so forth, can be very costly. As well, it can be very challenging to be residing at a space-limited location to deploy. In addition to that, the truck roll cost is significantly, because each individual network function or each individual box needs to be connected via fiber or networking cabling. That's an area which requires 100% touch, not zero touch, 100% touch in order to actually deploy or reconfigure or configure the network. Looking at the right side, so not only the size is a matter here, because we are also combining the compute resources, networking, load balancing, all into a small footprint. But the aspect for using an SDN framework in combination with computing and an SDN controller, or multiple SDN controller, and multiple virtual network functions, it makes it much more scalable. So that means that any virtual network function can reside at the service provider edge. It could be virtual BNG, it could be virtual SDN, virtual provider edge, virtual cable access point. These are all leveraging the same physical hardware right at the edge, because it's all scalable and fully connected internally. Numbers are important. Therefore, looking at the comparison, we're reducing the footprint and the total cost of ownership completely. So there is a cost savings on the rollout, and in particular when you see the uptake in deployment of universal CPEs where you need this aggregation points. This can be quite cost savings for the service provider in order to roll out these services. And these are significant numbers. If you look at the overall cost, space, and power, these are the elements really which are a challenge normally at the edge location site. A telco closet has only so much space and so much power available in order to operate all these different network functions. And of course, the high number of less costs, the significant in this 89% is the cost savings for operations, meaning all the truck roll to do the field deployment. And then don't forget, typically when you do a deployment on a traditional architecture, just the SFP, QSFP28, all the different network interfaces of fibering and the cabling, it's not a small portion on the deployment cost. So we're saving all that because in our case, it's a fully integrated solution using an SDN framework. And also we're eliminating the potential of a failure when you have dedicated fibers and networking using a cabling infrastructure. So this is reducing also an additional point for a failure. So that's a summary on what we're trying to bring to the market, helping the operator to go to the market quicker in a more cost-efficient way, deploying the network.
Thank you, Sven. To summarize today's presentation, we would like to highlight the following. The HTCA platform, as presented today, offers an all-in-one, scalable, zero-touch, software-defined MEC platform. It leverages Intel Silicon for both compute and networking. The HTCA platform is ready to deploy. To get there, NoviFlow is taking the system integration responsibility for the software stack. You may use an existing VNF from a list of already integrated and validated partners, or engage with us and let us know what you would like to see on the HTCA platform. The platform is also future-proof. The entire layer 2 to layer 7 stack is programmable. The switch blades are built on the Intel BAREFOOT Tofino chip, allowing us to update the packet processing in the silicon as requirements evolve. A good example of this is how NoviFlow recently added SRv6 support in CyberMapper and NoviWare. Everything else runs on Intel x86, allowing the functionality to easily evolve as requirements evolve and change. We estimate the HTCA solution to have an 89% reduction in CapEx compared to traditional standalone servers, load balancers, and switches. We also estimate dramatic OpEx reductions from power, space, and O&M. And thank you very much for listening today.
Okay, so we have our first question here, and it looks like this one is for Jesper. I'd like to start with. There are a number of different MEC solutions out there. Why should I buy your MEC solution? Jesper?
Yeah, thank you. The Lanner and NoviFlow MEC solution includes a programmable networking component based on the Intel BAREFOOT Tofino silicon. And most MEC solutions do not include networking. And furthermore, the Intel BAREFOOT Tofino allows you to run key networking services directly in the switch silicon, such as load balancing, packet brokering, and application telemetry at terabit speeds. So because it's programmable, it also allows you to evolve the networking functionality through software and not by having to replace the hardware. So Sven, anything you want to add to that?
Yeah, the fact is this is a platform which is a true software-defined architecture. and it provides zero-touch provisioning capabilities, what has been required at the edge compute sites, and therefore it's the optimum solution for edge deployment.
Thank you both. And so moving on to our next question, what applications should I put on the MEC platform? And why is it better than deploying high core count servers at the edge?
Yeah, thank you for that question. You know, as we presented earlier today, you know, with the Lanner and NoviFlow MEC platform, you have a dramatic reduction in cost, footprint, and power compared to these traditional solutions deploying servers and switches separately. Furthermore, it eliminates the cabling associated with interconnecting these discrete components in a traditional solution. And then finally, I want to add that with the NoviFlow VisualAnalytics software, the user gets an end-to-end view of the solution for operation and maintenance purposes. And Sven, anything you would like to add here?
Yeah, you can consider pretty much any application as a virtual network function, what typically would leverage commercial off-the-shelf hardware for compute, but can also leverage open programmable networking and using OpenFlow MP4 as the interface for SDN capable platform. In fact, you don't need to be an expert in P4 programming, as the combination of the Lanner and NoviFlow platform exposes an API which can be leveraged by the application to use the networking capabilities.
Interesting. That's great. We've got another question here that is quite interesting. It's how can I operate and manage deploying thousands of these MEC platforms?
Yeah, I'll take that one. So this is where the NoviFlow VisualAnalytics software comes in. You know, VisualAnalytics will upstream important events in the platform to an NMS system that sees the entire network. And once alerted, it will allow the user to remotely log in and dig into specific events to assess what's going on inside the MEC platform. And it allows you to troubleshoot and identify problems and then take actions remotely. Additionally, and this is even more important, through analyzing the events and measurements recorded and stored in the platform by VisualAnalytics, this is done in a time series database, you're able to perform preventive maintenance on items such as power supplies and fans. And on the compute side, you know, you would manage the resources with, you know, very well-known and widely used tools like OpenShift to manage your VMs and containers that provides the virtualized services. Anything you want to add, Sven? Or?
No, this is really the key element of NoviFlow virtualization tool, which optimizes the platform for deployment. So it's really well set, Jasper.
That's great. And we've got a question here about public cloud. So how does the NoviFlow Lanner MEC solutions fit with different public cloud MEC offerings from companies like Microsoft or Amazon?
Yeah, this is a really interesting question because there's so much, you know, being talked around this out there. And the Lanner NoviFlow MEC solution is for the carrier's own virtualized network services and applications that they need in their own network and will offer directly to their customers. The public cloud MEC solutions will host all the non-carrier services and applications. And over to you, Sven. Anything you want to add?
Yeah, so the biggest trend for 5G deployment and the initial rollout will be for the private 5G infrastructure. And that private 5G infrastructure requires on-premise edge compute hardware. And the reason is the hardware will reduce latency in the network. but also provide resources right at the edge. These platforms may connect to a public cloud, to other hybrid services for Amazon or for AWS, but ultimately most of the processing for artificial intelligence as well machine learning will need to reside on premise because of reduced latency in the network, and it's really critical to have that at the edge device on premise rather than pass it all the way down to a public cloud infrastructure.
Oh, thank you. That's really interesting. And I'm afraid that's all we have time for today. Now, if we didn't get to your question, our speakers are happy to follow up with you after the event. And also wanted to make our audience aware that there will be a replay available in the next 24 hours. So I'd like to thank all of our speakers for a very informative session. That's all from us today. Thank you and goodbye.